What's your name again? That was very nice. So it's always daunting and exciting to come back and visit Alma Mater. I did get my PhD across the street. I had lunch with one of my advisors yesterday, Clark Robinson, who's tying his shoelaces in the second row here. And we look back to think that we probably no one left from our era, which is one of the reasons I'm going to give the talk I'm going to give. Because when I've come back to Northwestern and talked, I was really nervous. Here I am talking in front of all my old advisors, and they're going to judge me and say how well they did. Now they're all gone, except for Clark. And therefore, I don't care anymore. So I'm going to give a talk like I've never done before. I'm going to give a talk where I ask you to help me. The word musings in the title is there on purpose. I really want to think about mathematical modeling and sort of what we, well, let me just present it. So there are alternative titles. How do we know what we think we know? Which I think is sort of what modeling is all about, and I'll give some examples of that. Or one of the catalysts of this, so with another one of my Northwestern mentors, Don Sari, I'm on the National Academy of Science Math Board. And our job there is sort of to give math guidance to other government agencies, including the NIH. And the NIH has recently added to their proposal guidelines the demand that modelers justify their model and give a sentence about how they know it's true. That's, nobody knows that question. So that's what this is about. We're going to figure it out together. Okay? Or I'll make some suggestions and ask for help. Okay? There's my email address for those who want to go further. By the way, I just wrote a history of the Bach group, and anyone would be interested in that, I'll be glad to send it to you. A very short honor in a book honoring John Howland on his 195th birthday or whatever it is he just did. So and then the question, just the role of modeling. So so there are some of the catalysts for this. Let me look at the middle equation. That's a picture I had on before. It's what I ate for breakfast yesterday at the Orrington Hotel. Wasn't very good, but you can eggs Benedict and coffee and cream, and so 5 years ago, whenever we look at food in a restaurant or anywhere, we sort of think which of this is good for me and which isn't. Okay, so in this picture, if I asked that question 2 years ago, I would have said, eggs are full of cholesterol. That's one of the worst things for our body. I think I should eat the potatoes and bread and maybe skip on the eggs. Well, last month, the medical profession decided that was bullshit. And in fact, we should throw away the bread and potatoes because that's the horrible carbohydrates and love and eat the eggs. Because that's cholesterol, but apparently food cholesterol is different than blood cholesterol. This is science. Why didn't we believe those bastards all this time? Right? Okay, why did we change what we eat? So I want to talk about that a little bit. How did they get there? How do we avoid that? And of course, I'm also a proud academician, so I will talk a little bit about my own work and how I came to ask some of these questions, or others came to ask some of these questions about my own work. Can you hear me okay, by the way? Okay. So that's breakfast. So, and this is the article that February 20th, New York Times, and it's worth looking at. I don't like to have people read slides. I ain't going to read it for you. So if your English is not your first language, you can't read English, tough. So I'll assume also you can read quickly. So mostly stuff I've been saying, all the things that I love I couldn't eat before, now I can. I am so happy. Except for bread. I really do like bread. Okay? I had some great bread at Boltwood yesterday. If any, I have a word from I get a kickback if I, just like authors, if I advertise places I like. So, a lot of this comes from the whole method of sort of loose correlational observational science. And I want to think and talk about that a little bit and probably piss off some people in the medical school. But I think, and part of this had to do with egos. Egos. The people who really fought. There wasn't a very good study of the cholesterol stuff. And it was really prompted by a couple of people who were very powerful scientists and pushed their will on society. But still, so there are things out there. Is what you're eating now good or bad? What about the carcinogens in the Diet Coke I'm drinking? Anyway, I may find out 4 years later it's the healthiest thing I could be doing. So when do we know? Okay, fair enough? So let's start at the beginning. Just a very good place to start. And so I do have a banner that I believe in wholeheartedly. Basically, everything's a system. And if you ignore that piece, you're going to get something wrong, as people have dramatically throughout history. And getting things wrong are unintended consequences. Okay? So, I think the most striking example in my lifetime is DDT, right? We got these bugs that are destroying crops. Let's kill them, okay? Then we'll be okay. Well, the food will be, the problem was, of course, it did work, but the bugs died, but the critters that ate the bugs died, and the critters that ate the critters that ate the bugs died, and we almost lost the American eagle, and it had dire consequences. Rachel Carson and people came to the rescue. And maybe DDT isn't so bad in moderation. We are now starting to use it in the fight against malaria, but understanding its role and not just indiscriminate overuse. One of my favorite examples, right? Some guy wanted to like to hunt rabbits. When he moved to Australia, he brought a few with him. Sometimes in a related lecture, I've got whole pictures of the devastation to Australia that rabbits have done. More closer to home, many of you are parents. Your kid gets sick, starts crying of ear infection. You demand of the doctor the strongest possible medication so you get this over as quickly as possible. Okay, that has unintended consequences in terms of, I do think, and part of my research is based on this, that when I was 40, I thought nuclear destruction was going to end the world. I really do believe it's going to be the drug-resistant antibiotic that's going to wipe us out, and that's something we should worry about. And one little thing, one piece that almost everybody in this room is probably guilty of is using antibacterial soaps at home. Okay, those are drugs. They actually help in the proliferation of drug-resistant bacteria. I had an experience here at Northwestern I don't think I've ever shared with many people, but in 1970, 4 incredibly interesting things happened to me. June of 1970, I defended my PhD. I got my first job, my dream job at Berkeley, California. I had my second kid, who now teaches at Yale. And I got cancer. Very serious carcinoma of the right testicle. Okay? So I went to Northwestern Student Health, and I said, there's something wrong here. And the guy looked at it and said, oh, yeah, that doesn't look good. I think we'll do a biopsy. Of course, right? You want to see what it is? I said, well, this is all very startling. I don't want to do it. Let me just go home and understand what's happening to me, right? I'm a healthy 25-year-old, and the fact that I'm about to die maybe scared the hell out of me. So I did go see another doctor at Northwestern at Evanston Hospital, who looked at it and said, yes, that you do have teratocarcinoma, but if you do a biopsy, it'll certainly kill you. because right now your tumor is encapsulated. And if you break that capsule, you'll be in trouble. Okay? Here's a man who saved my life by thinking systems. And there's a little bit of that, if I can, I'm going to stretch a little bit and get into controversial politics. It may be that if we destroy ISIS as it is now, this concentrated group, what we'll end up doing is spreading them over the world in a way that made make it harder to contain. I mean, there's some thought of that in knowing where your enemy is not a bad idea sometimes. And it's about subtleties of unintended consequences. I'm not saying I believe that, but it's certainly worth thinking about. Plenty of other examples. In Chicago, I watched them tear down the high-rises along the Dan Ryan when I was growing up. Okay, but that didn't solve anything. It just moved the problem around. So this is about building. How do you think systems? The only way I know is you build a model. You identify what's important, the main actors. You draw a diagram that says this is A is connected to B, and you try and understand the system as a whole. Okay, and then if you can, you sort of quantify some of those connections and start running with that. That's sort of, model building is now what my life is about. And it's just a sort of aside. So my thesis was in pure math. Basically, one of the first uses of chaos to understand systems of differential equations. But throughout, little by little, I've got sucked into more how to use math. And I was a member of the econ department. I'm a member of much of my work is in epidemiology. So I've come to care a little bit about not just building the model, but understanding when it's right.
One of the key words on that last slide, you had causal.
Yeah.
Because most diagrams are more associations and not necessarily cause.
Yeah, well, that's an important piece that I want to come back to. But this may be my most, for me, the slide I've thought the most about. Why do you build it? What can you hope to gain from a model? Okay, this will be on the test. And there's a lot of pieces, so let's linger on it for the next hour or two. First, there's a lot happening, and a model can help you. No, taking a picture of this won't, that's cheating on the test. That you cared enough to do that, I appreciate. There's a lot happening, and a model can help sort that out a little bit. Collecting data. So much of my early work, the work I'll talk about today was about the spread of HIV. And when HIV hit we understood what was happening in the late 70s, people ran out to collect data to try and figure out what's happening. They asked all the wrong questions. It didn't help at all. They asked very deep and penetrating and personal questions, some of which helped and some of which didn't. But having a model to understand what would really advance what we know about the disease would have been far more important. We went back and asked the right questions later, but not at first. The third bullet is the one I care about the most, and it's what I built my life on. Using models to understand things you can't see. So the paper I just finished was about asymptomatic gonorrhea. Gonorrhea we teach gonorrhea in all our differential equations course. It's sort of the simplest disease to study in some ways because the folklore is people are immediately susceptible after they are cleared of gonorrhea. But in fact, there are two kinds of gonorrhea. There's symptomatic and there's asymptomatic. How do you treat something you can't see? Well, the only answer I know is you build a model and try to ask how the model, how changing some parameters you don't know in the model, how those change. When do the right parameters help the model best fit the empirical data? And that's a start. Okay, and that's what we just did. And the bottom line is, at least at its very tentative stage, is that probably gonorrhea is close to 100% contagious, which is a little startling, but sort of known before. But now, now that we've been able to include things you can't see, the other thing I'm working on is cigarette smoking, which is a little bit, people focus on cigarettes that focus mostly on getting people to quit. But I think it might be more interesting to understand how people start. In particular, there are a lot of government programs, policy on trying to stop people from starting. Who should they focus on? There are two ways you can start. One is through contagion. You get it from your classmates. The other is, all other possibilities. Watching John Wayne smoke. Or even maybe you just try it because that's the kind of person you are. Which one of those? So we have incredibly good data about who smokes at what age, but we can't quite tease out how they got there. But if you build a model, and if those are the parameters in it, you can fine-tune those parameters to try and understand the impact of both of those pieces. So it's about building using a model, and that's the part I care most about, and I think that's an important use of models. Epidemiology, there are a lot of experiments we can't do in epidemiology because they'd be unethical or maybe not even helpful, but if you have a toy world to play with. So I'm building a model on the spread of crime. And maybe think of it as SimCity for criminologists. So you can go in and maybe get some feel for what different manipulations will do. Of course, it helps in comparison, contrastions, help you formulate the right assumptions. And then forecasts, right? An important use of models recently has been to forecast the spread of Ebola. How long will it last? How many people will it kill? Boy, did we screw that up. Okay? It ended up being, it was a very serious and still ongoing epidemic, but it's just about over, and it's the actual death toll is orders of magnitude less than we feared. Why did we get that wrong? I want to think about that a little bit. I have some ideas. Well, we wouldn't do modeling if they didn't work sometimes. And there's some success stories, even starting 100 years ago with Sir Richard Ross's malaria model that showed you didn't have to kill every mosquito. You didn't have to vaccinate every person to beat a disease, okay? There's herd immunity effects, and you get certain things under a certain threshold. What that threshold is would be important to know, okay? Vaccination strategies. The US and Britain have a lot of very good mathematical epidemiologists. They both built models about rubella. And what vaccination techniques would work better. One of the two suggested focusing on every child. The other said, wait till they're 14 and then vaccinate every girl. Two different models came up with two very different pieces of advice. And we now know that, in fact, the right is some combination. And if you choose one of them and don't get above the threshold, they'll do more harm than good. That's a pretty striking result from just the modeling and understanding, okay? So I gave a whole bunch of models, and maybe the question is, does the model do what you want to do? Depends a lot on what you want to do with it, okay? And it's, if you want to use it for SimCity, that's one thing. If you want to use it for policy, telling people not to eat eggs, that's another issue, okay? I'm sure I'll mention it later, but I think one of the more interesting, we're in a building with transportation, and we're also in the place where NetLogo was born, okay, for which I am eternally grateful, to say the least. And there's a lot of fun exercises in that logo, and one of which is the transportation model, where you can actually watch traffic jams happening without an accident happening anywhere, just as a function of the density and speed of cars. Well, there's real, I mean, you can, if you go on the highway, you can see the, on the entrance ramps, there's stoplights that try to control that. And I think there's a policy that came from people understanding the modeling of controlling the density. And I think that's a beautiful example of where at least I don't know at what depth the model was, but that's something that really works. So I have a Michigan and complex systems has sort of a philosophy of model building. And it really is starting simple and building up. One problem with a model and knowing what, even a computer program, right? So if you're building a computer program, there's a big question is, did you get it right? Is there a glitch in it that's giving you a mistake? How do you know? Well, my way of thinking about it, and I think of many of my colleagues, is you start simple. You build a simple model, something you can dock and know whether it's right, and then you build onto it, make it a little more complex little by little. I think that's a good way for all modeling, even for disease spreading. So Bob Axelrod, my dear colleague, calls it the KISS principle. Keep it simple, stupid. Okay? And, capture the, and then build from that. Yeah, so there's the KISS principle in action. So there are models and there are models, okay? And I'm going to talk about these classes. And so I'll tell you the bottom line. This is a progression that I think should be done. It's not only a list of models, it's sort of a list whose ordering seems to make sense to me. So most of the models, including the models about what we should eat, are pretty much correlational models. Okay, you get a bunch of randomized clinical trials. You have some people who eat cholesterol and some people who don't, and you see what the effect was. Okay, those are another word for that. One thing that really peeves me is that the names they give these oversimplified correlational models. It's the holy grail. It's the golden rule. It's evidence-based medicine. That's proof by intimidation if I ever saw anything like that. Okay? And I think stopping there, if you don't have to, is a huge mistake. And so I really care about going to mechanisms and understanding what makes these things happen. What is it about cholesterol that's good or bad? How does it interact at a cellular or lower level? And it's too tempting to just say a little word in this, well, I will a little later, about simple versus, what does complex systems mean to me? Okay, this seems like a good place to make that comparison. So when I first started working on contagious disease spread, still most of the models took the biostatistic approach, and it's very linear correlation. You made a list of people and what they did, and then a list of what happened to them, and you did a checkbox, and I'm oversimplifying, but that's as speaker I get to do that. And you came out with things like risk factors. And a lot of problems with this approach. If you take any statistics, that there's assumption of independence. Well, my getting, a heart disease may be independent of your getting it, but my getting the flu, excuse me, is not independent of your getting it, okay? As you pointed out, it's about correlation, not causality. Misses indirect effects. Okay, when you do these, the world's much more complicated. But if you assume yes or no and don't worry about indirect effects, you're going to miss something. And I'll say more about that. The outcome variables, if you do some of these, like risk factors, odd ratios, they change over time. How could that people make time-independent decisions? Independent. So I said heart. I almost said cancer. But I think we now, and I certainly believe, that cancer we're seeing it more and more as a communicable disease, right? HPV, for example, cervical cancer, closely related to human papillomavirus. Okay, in fact, there may be almost one-to-one connection. Other cancers are more and more, the connection between bacteria and viruses and cancers is becoming strikingly interesting. So that cancers, I think, may no longer be a disease in which we can assume my getting it is independent of your getting it. And Paul Ewald is one of the apostles of this and has some great books about it, but it's coming out more and more. Well, I don't know. There's a process for building a model, and that's too complicated. So let me give an example, okay? So this is a class. Many of you have seen this, but I'm going to do it anyway because I'm a teacher. So what about, one nice thing about disease spread, studying epidemiology, is there's a canonical model that we start from all the time, okay? This is for contagious diseases. So this is the process. You divide people into 3 groups, those who have the infection, those who don't but could get it, and those who at least temporarily maybe have had it and can or cannot get it soon, okay? And then you build in the arrows. So people when infected and a non-infected meet, there could be spread of infection. Once you get it, you can recover. If you lose, okay, those who recovered may or may not lose their immunity. As I said for gonorrhea, it's roughly thought that you're immediately susceptible afterwards. Turns out that's not true, because in fact what is really true is that there are many strains of gonorrhea, and you are probably, very immune to the strain you just got, but completely susceptible to all the other strains. So these, part of the problem with oversimplifying. But keep it simple, stupid. First models. So if you look at these models, the next step, as I said, is maybe quantify them. And here I think are the main parameters we might care about. I said it's contacts. So how many contacts are there? Given a contact, what's the probability that infection will spread? And then there's the recovery part. What's the ratio of recovery? And then, you may get hit by a truck on your way to the doctor, or you enter the population somehow. So some demographic parts. So I'm now going to draw the equation of, so how many new infections are there in some time delta t? Well, this is contacts per person in a year. This is contacts per person in the time period. This will be on the test. This is total contacts by people who are not infected, okay, in time delta t. This is the probability that the person you meet is infected in the simple world. And then not every contact infects. So this is the epidemiologist physics envy equation. Okay, this is the so-called force of infection, and then you have people leaving disease either through recovery or background death rate. So that's it. That's in this simple model. That's the equation, and if we can analyze this, how I analyze this, the same methods work for analyzing far more complicated equations, as I'll show you in the next hour or two. Okay. So if you go back, at the top, here's the equation again. I'm assuming a population, no background, no disease death, that the population is constant. Again, keep it simple, stupid, first time around. So I can substitute, for that's got y and s in it, but s is, n minus y. So if I put that in the equation, arrange and simplify, I get this simple equation for the change in number infected. Okay? Well, this is one of the most famous equations in pure and applied math. It's the logistic equation. It's quadratic because of this y term here. Okay? It's the basic equation of population growth. And a lot depends on this term in brackets. Okay? So if this is negative, then this whole thing is going to be negative, and this will always be negative, and the disease will die out. if this is positive, this constant, then there'll be some times that this is positive, and the disease will grow for a while. Okay? Graphically, it looks like this. Okay? So I'm graphing how many are infected by the change. So in the one case, when y is positive, the derivative is negative, which says y decreases. In the other case, there's a range where y positive, where it increases to the endemic level. Okay? There we are. That's to keep it simple. And so we could actually look at that and come out with, remember that term in brackets, whether it's positive or negative, told me whether the disease would die out or not. And so that leads us to this threshold or tipping point. And this is the word for mathematical epidemiology. If this is less than 1, the disease will die out. If it's bigger than 1, the disease will stabilize at a positive value. It's an input-output, okay, fraction, okay? And it's called the basic reproduction number. In demography, it's how many daughters does a woman have in the course of her fertility. If that's bigger than 1, the population grows. Less than 1, the population dies. Here, it's how many infected does an infect in the course of his or her infection. Okay? So, now, I really want to model the spread of HIV, and I wanted to do that back in the 80s, right after it hit. So I've got to get beyond that model. So what are things that I care about? Well, first of all, people are different. Actually, I'm looking at this overhead and wishing we're in a different place. This is sort of how I envision a progression of models. And again, it's close to the bottom line of what I want to say. You start with a simple macro model like I just showed you. And then you put in more complex behavior to capture reality better. Okay? Things like people are different. In my model, you're either susceptible or infected. I didn't worry about age. I didn't worry about how promiscuous you were. I didn't worry about what sex you are. Okay, that has to go in. And then once you get some understanding of that, I think you have to begin to understand mechanisms. Why is this happening? And that's going to the micro level. First looking at individuals and their behavior, and then going down to cellular, nano level, even genetics. I think if I want to say, I'll tell you the answer to my question, by the way, in case you want to leave early. How do you know when a model works? Never. But you can come closer and closer by looking, finer tuning mechanisms. Stopping at the top is dangerous. You sort of got to stop, but if you do, you should warn people that you're doing a correlational analysis and not a causal analysis. And I want to give an example of my own work on this process. Okay, so I get to spend a little time on my own work. I have till 2 or 3, PJ? 1?
Till 1.
So here's the model I presented. So just a word on how complex system enters. This is what I would call a simple system. And it has these 5 ingredients that make it simple. Okay? Everyone's the same. We focused on either equilibrium, whether or not the disease was endemic or not. There was random mixing, right? The probability meeting someone infected was a proportion of infected in the population. There was no feedback, no learning, no adaptation. It was deterministic, and there was no connection. This was a macro model, nothing about the micro. And usually my whipping boy is economics, because these are exactly the assumptions that I teach in my econ courses, right? People are roughly the same. There's economics is general equilibrium, microeconomics, general equilibrium theory. We rarely worry about structure, who meets whom. There's no adaptation. It's like advertising and school are useless. This is, the simple thing we teach our graduate students. It's usually pretty deterministic, and there's no connection. The microeconomists at Michigan don't know the macroeconomists. Okay? And in biology, all this is true also, and in Michigan, they've divorced. The micro people are in one building, and the macro people are in another building with different, Crazy. So I think of, but this is where we start. It's a good place to start. But to me, and it helps us gain insights because we can actually solve these mathematically. We can calculate tipping points. We get conclusions. Okay? So in epidemiology, the conclusion is there's a basic reproduction number, and it'll determine whether or not the disease dies, and it helps you tell you what to focus on. In economics, there's also a conclusion. It's in the last chapter of every econ text. It's called the Fundamental Theorem of Welfare Economics, and it's that markets always work. Okay? So to me, complex systems about asking, are these true? If we put in realistic ingredients in our model, do the simple panaceas we suggested still hold? Okay? And so you go from this to that. So in a nutshell, that's what I think of a complex system. It's a model that has ingredients of including diversity. Scott Page, thank you. Putting in real dynamics, that's sort of what I care about the most. Having networks, this is a place that Northwestern is famous for. Having people learn, and having emergence of macro behavior from micro assumptions. Okay, so for me, when we hire somebody or think about complex systems, it's these pieces that I think make the difference. So, taking a step closer to HIV, this is a little better diagram. It's two things about HIV is it has stages of it, depending on your CD4 count, and there are different behaviors. And I'm thinking this just to keep it simple, and this is more or less looking at San Francisco early data. So I'm assuming male to male sex, but different different levels of partner formation. Okay, instead of random. Right. And what did I do? A problem. Okay, this will take a half a second. I think we'll be back. I obviously, whoever is running this machine didn't agree with me. Almost there. If you didn't get the talk up to here, here it is. Okay, bump. Okay? So the model's not that more complicated. I've got different stages. This is a model actually where I don't include, for exposition's sake, I'm only including the stages complication, not the behavioral ones. But just with this model we can still analyze completely. From my own work, there's the basic reproduction number. It's still basically like it was before, but it has a little more contexture to it. And if people have different contacts, you still get another one. And it's for me very pleasing because it uses a lot of the differential equations theory that I learned from Clark and people when I was growing up here. But what I want to do is, in this model, I want to focus on stages. So beta 1, beta 2, and beta 3 are the key parameters. They're the probability of infection when a person who's susceptible has a contact with people either in stage 1, stage 2, or stage 3. Okay? Stage 1 being the first month or two, so-called primary or acute infection. Stage 2 being later in the, and we knew beta 2 and beta 3. Because you can do data on that. I mean, there are people who had gotten HIV from drug transfusions who had regular partners and who continued to have sex. And so we could really, and those numbers were incredibly small, 0.01% probability. It's beta 1 we didn't know, and we can't see because often, at least in the situations we looked at, one didn't know when they got it or who they got it from. So this is a case where you build a model And you put in different betas to get different beta 1s to get different curves. Okay, I'm being a little heuristic here, but allow me. Here is San Francisco in that early period. Now it turns out that they didn't keep, again, most cities, that's Chicago up there by the time they started collecting data. Most cities start collecting data far too late, so you don't catch the beginning. But in San Francisco, they had a hepatitis C epidemic at the same time, in which they actually had blood samples from the whole population and could go back and look at them and really trace the spread of HIV. So the point is, we needed to get beta 1 pretty large to come close to have the model fit the real data. And so we published this with great pride to say that most people get HIV, get it from someone who just got it. And there's a model conclusion. And were we right? Washington Post thought so. They published a nice long article with pictures. But they, as they should have, had people who agreed with us and people who didn't. New York Times didn't agree at all and didn't bother publishing it. But so I want to think about, did we know that? The model I presented is full of, it's not a correlational model, it's a causation model, if I may. But it's got some correlation to it. To calculate, I use maximum likelihood estimators to get the optimal beta 1 to fit the data. How can we really know it's right? Jim York was a very vocal critic of what we did. Famous mathematician who was founder of chaos, and in some sense, my thesis was built on things that he introduced to the world. So this is sort of where do you go from how can we be a little more certain? And I have an answer. And the answer is, as I've said before, keep adding things to the model little by little to see if you can break this. Understand when it occurs and when it doesn't, and then go into mechanisms, go lower down, go into figure out what's happening in the body, okay? And so why is it reasonable? It's sort of reasonable because of the so-called bathtub-shaped curve of antigen in the body, okay? The virus comes in, it takes a little while for it to get, and then it just, like your flu, it gets very high, and then the immune system kicks in, sends the virus load very low for a period of time until the virus destroys the immune system. And by the way, this is another period of high transmission, but many people were a little sick to be in the transmission process, or well known to have HIV. So I wasn't focusing on that piece, and I still caring more about the primary infection. But that's a schematic. So U.S. News and World Report showed this diagram, stopping AIDS in its tracks, right? And there's a picture of me and my two coworkers talking about how the policy implications of this work, how building might help in how a vaccine might work. There was one immediate policy implication. The week we presented this to the world, it was also announced that someone had devised a household test for HIV. And we're at least able to say, don't believe them. Because these are very crude tests, and they miss primary infection. Okay? And so this test, it's far more important to know something about your partner than it is to do this rather coarse test that will completely miss the key part of your body doesn't quite know that the virus is in you, and so how can what factors do we need to bring into to understand this acute infection transmission? Well, and what are we missing? Well, there's population patterns. There's different kinds of sex acts. there's partner chains, there's social networks. We assume this model, something closer to random mixing than really occurs. There are a lot of assumptions there, right? And so somehow we had to go beyond those assumptions. And here's what, I showed you the diagram, the schematic. Here's HIV in Atlanta, where in fact different shapes for different sexes and different sizes for different levels of activity. You can see it's not random mixing. It's a very complex network that the kind that people here know well about, and why putting networks together with but it did. So the point of the model, however, it made a suggestion, and this is what I think the first step should be. Here's where to look. So Waller and her group went in Uganda and again studied a population of discordant couples in which people were more open about their sexual activity, and they could collect very striking data for the whole and then keep track of what's happening over time. And they did find a 12 times higher transmission in that first from people who were just infected than people weren't. Step in the right direction. This was heterosexual, not homosexual, but again, indicating a little more that maybe we were right. But again, the next step, right? Here's the picture we looked at. Here's a picture that just came out in New England Journal of Medicine. Boy, now, I said we got to know mechanisms. We really have gotten, people have been focusing on this. Here's what that curve really looks like. The amount of virus in the blood. It doesn't quite go to zero. But, there are bodily, there are things happening in the body that have very strong connections with different stages of HIV. And we could now take a person and really understand how long it is since they've had HIV by looking at plotting, taking samples and really understand, this is far more powerful when we're now getting closer and closer to mechanisms. One of the things we didn't do, however, in the first thing that would be a next step is to put behavioral change. I really do think one of the real failings of almost every model I know is refusal to include behavioral change. It's difficult. It's hard to do. Okay? We said, okay, what's going to be effective behavioral change? So we had, and we did it exogenous. In fact, people change endogenously. But let's assume people switch for some reason. How will that affect the spread? So we have a high mixing group and a lower risk group, and sometimes a high only mix with the high, and other times a high mix with a low, or the low, okay? What effect does changing those rates have? And it has a big effect. This is far too complicated, but this is sort of how much transmission comes from primary infection, depending on how much partner change there is, okay? And the more partner change there is, in fact, it's much bigger, as you might expect, a much bigger role for primary infection. But this also tells us when it's less important, okay? And that kind of fine-tuning, I think, is an important in the step of being able to understand how a model can, you need to know when your model, under what environments is your model right, and in what environments is it more right, and when is it less right. This is, again, sort of going into how the population structure affects it. But this is the one I really want to show you. This is, I think, the creme de la creme. Everybody knows HIV virus is very mutative, right? Its mutation rate is gigantic. But it turns out it's not random mutation, they're patterns. And this is, basic genes or clusters, genomic clusters that are sort of in the virus that are sort of triggered as you progress with the infection. What this says is we could, if we take out a sample, we can look at the virus do a genomic analysis and know how long that person has had HIV. Okay, just by seeing what parts of the genetic tree of the virus are by breaking down the tree. Okay, and sometimes we can even, with more information, get some feeling on who they got it from. Okay, as you can imagine. And the key part, and one of the main reasons that the primary infection is more believable, is that the virus has a couple roles in life. One is to get transmitted. The other is to do what it does to the body. Those are different, and it turns out that the shape of the virus that promotes transmission is very different than the shape of the virus that does what it does to the body. So, many reasons it makes sense. And then finally, in the article in New England Journal of Medicine, this is a study of basically saying it probably is primary infection. Okay, here's our work. We were among the first. It's Koopman, Simon, and Jacquet. This is 97. We came up with actually sort of lower probabilities of transmission than many of the others, right? We're talking about 50%, 30 to 50% probability. But we still don't know. It's still too simple of a model. But I think we're much closer to knowing by going deeper. Okay? Network, one thing really not included in the modeling is the network stuff. Real networks of people interacting sexually are far more complicated than anything we can model simply. But as you know, they're well studied. Here is the model of how many people have how many partners. Many people have few, a few have very many. And this distribution is so-called large tail distribution. Okay, it's a important complex systems distribution in which there's no mean. Okay, and from this comes the fact that R0 doesn't work in these models. So I really do think this behavioral change bit. So why do I think we screwed up Ebola? We didn't take into Ebola forecasts. We didn't really take into effect the changes that would happen, the behavior changes. People in West Africa really did stop, throwing themselves on tombs of deceased. The world came in and intervened. We didn't put any of those in the models. Okay, there were both positive and negative parts, and it's true in HIV. I mean, my model behavior change is so primitive and it's just, my colleague Jim Wilson in Maine basically used genetic algorithms to look at behavioral change among lobster fishermen and their strategies, and I think this is an area very ripe for complex systems work. I'm running out of time, and not running out of things to say. Let me just say a little bit about the opposite end, the Holy Grail. We're in an age of big data, right? And it's the buzzword. Many of you here are enamored with it, maybe even enslaved by it. You can tell I have some cautions about it. I mean, big data, you're looking for patterns, you're looking for correlational things. I think it's a great way to start, but it's a little scary that people may stop there and tell you don't eat eggs. Okay? There's besides the food, there are some very dramatic. So these, the kind of things I'm studying are sort of cohort studies where you look at the incident, you have control groups. They can be careful, but they're really about correlation, not causation. And you could get up. There are some really interesting correlations that work very tightly. Here's a correlation between chocolate consumption and Nobel Prizes. Okay, and it's tight, 0.99, right? Because we should have chocolate for snacks. Here's the one between the murders in the U.S. and the market share of, yeah, okay. Here's one between the marriage rate in Kentucky and per capita consumption of milk. Okay? You really have to be careful about correlation and causation. And there's even a website called Spurious Correlations that I stole some of these from. Though I must say that chocolate articles from the New England Journal of Medicine, and they were a little serious. Okay? So I do think this method is somewhat theory-less. It is not very system-like. It sort of focuses on one treatment at a time without worrying about spillover effects. It assumes a lot of linearity, a lot of independence. And so it doesn't apply very well to infectious diseases, and I'm now even throwing cancers in. Ulcers, which are now an infectious disease, because in fact comes from the Heliobacter bacterium, as you know, as a recent Nobel Prize illustrated. It can only use observable data. A lot of things we care about are unobservable. It usually only works with averages. There's Robert Kaplan, who's the head of OBSSR, behavioral science, anyway, in NIH, did the study where if you looked at random clinical trials before 2000, 57% of them said something's wrong. After 2000, only 8% of them gave a warning. What happened then is the NIH demanded some control over the clinical trials. Okay. Probably a question I find especially interesting are mammograms and breast cancer. Okay, so NIH, besides telling you not to eat eggs, has been telling women that they shouldn't have mammograms because they don't help. They don't change it. How can you not want to know what's in you, okay? And yet these came from, this is a very controversial part, but it's very, NIH feels pretty strongly about it, or did for a while. And there are risks. There are risks of false positives and unnecessary surgeries. But women, and you can look at and see, you know, there are lots of easily visible problems with the samples chosen, and the alternatives. One group had forced mammograms every few months. The other group was doing what it did, including having regular mammograms. So it's, you know. But then the NIH said, okay, you guys are complaining so much. We're going to fund a bunch of modelers to see about mechanisms and understand the real, the systems approach and not this pure correlation approach. So they hired a bunch of university famous modelers, and their conclusions were the opposite of what NIH expected, that in fact they do make a big difference. A PhD student of mine, Kristin Hosmer, who's at North Carolina, I was on her committee, showed that correlation, you know, random clinical trials indicated that cigarette smoking has a lot to do with the spread of tuberculosis. But when she made a model that included indirect effects about who smoked, you know, what the communities are, she found it's twice as large, the effect. Okay? And that really, there's a policy thing there that really does say, if you want to beat TB, get more aggressive at stopping smoking. Okay? So I think, so, you know, validating a model depends on what you want to study. It's a loop. I think you start with simple, even correlational models, but you understand, you try to understand the mechanisms. You include sensitivity analysis. None of those mammogram studies that were correlational really talked about, you know, error. I'm exaggerating a little bit, but they were very sloppy on their error analysis, giving distributions. They really focused on the means. And finally, Indiana Jones, who said, "What? Beware of searchers for the Holy Grail." So, thank you.